Okay, so for this module, you're going to be given a set of rock weight data from scoria erupted during the 2008 eruption of Okmok Volcano, Alaska. You're going to use that data to estimate the porosity of the magma at fragmentation. From the vesicularity of those samples, you're going to basically estimate the gas content of the magma, which is represented by your calculated porosities from those little scoria samples. And as I mentioned earlier, you have to apply some assumptions to make this work in order to use those samples as a proxy for magma gas content. You're going to take your porosity data that you calculated to model permeability of those samples using percolation theory. And you're going to assume that that permeability represents the permeability of the magma as it reached fragmentation during that explosive eruption. And then you're going to answer some questions about how your results may apply to vesiculation in the conduit at Okmok Volcano. So I have a couple pictures here that I took during the 2008 eruption. The top one shows a big ash plume coming out of the caldera. So Okmok caldera is here where I'm pointing my mouse cursor. This is Mount Tulik, which is a little old dead flank cone on the side of Okmok. The ash plume is coming out from a cone inside the caldera. The lower picture shows that cone. It's called a monolix. It means the surprising one in the Atkin dialect of the Unangan people who live in this area. It created a brand new tough cone / cinder cone. You can see a little steam poof coming out from the interior of that cone here. This is inside of the caldera. So this is the cone that was producing this big ash cloud shown up here in this picture at the top. So just a reminder, I think we've talked about Okmok before. Okmok is located in the eastern Aleutian Islands. It's about 100 kilometers to the southwest of Dutch Harbor on Alaska Island here. In this map, you can see Anchorage is, it's about 800 plus miles to the northeast from Okmok. So the Aleutians are a really long island chain, and Okmok is just in the easternmost part of that. This map shown here shows a digital elevation model. Here's Okmok caldera. This cone I'm circling right here, this is a monolix. This is the source of the 2008 eruption. And all of these sample locations here come from the first part of that eruption. It's the first 12 hours deposited pumice, lapilli, and ash to the northeast on the island. And sample location that's noted here is circled by the red circle. It comes from inside the caldera. This is where the samples came from that you'll be using for this homework module. Here's a picture of what the deposits look like. You can see they deposited in this picture on an old layer of snow, which is great because we know exactly where the base of the deposits are. We know really a lot about this. There's no ambiguity here. The eruption deposits start right here at the snow rock interface. The first part of this eruption you can see here has some coarse-grained stuff in it. These are coarse scoria lapilli. These are from the opening part of the eruption, the first 12 hours. We think it was maybe subplinian in eruption style. It was highly explosive, 50,000 foot ash cloud. After time, it still remained explosive, but settled down a little bit, and the ash cloud was, kind of pulsating between lower elevations and 20 to 30,000 feet. The eruption lasted for 5 weeks, and the upper part of the deposits shown here are very fine-grained. You can see they look like mud. They're very, very, very fine-grained ash layers, and at least for this part of the eruption series, the eruption was phreatomagmatic and in style. Later on in this class, you'll learn more about this eruption mechanism and why it produces so much fine ash. But for intents and purposes of this homework module, you'll be concentrating on the lower layers, which are much coarser grained. So these lower scoria lapilli samples are going to provide a proxy for the gas contents and permeability of the magma when it fragmented. Here is an example of what some of these scoria lapilli look like. This is from a different location, but still the same sort of thing that erupted all throughout deposit area during the initial part of the eruption. So here's a 2 centimeter scale. You can see they look kind of lumpy. So these little lapillis are full of little tiny vesicles that preserve what the gas content of that magma was when it fragmented. And the permeabilities of these little tiny, these lapilli samples and their little tiny vesicles, how connected they are, gives an idea of how permeable that gas was when it reached the point of fragmentation. So how do you actually measure the bulk density to calculate porosity of a volcanic rock? Well, in this online class, we can't all get together in the lab and do this exercise, although the data you're going to use is from prior classes that were taught in person. But I'll explain to you how to do this. And if you have a rock sample and you have some wax parafilm handy that you might be able to use, maybe in your geology lab on campus, or maybe you can borrow some from the chemistry department, you can actually try this. It's actually kind of a fun little demonstration of density and buoyancy in Archimedes' principle. So the data for this homework module given to you was measured, the bulk densities were measured using Archimedes' method. And this cartoon shows you basically how it works. So if you go back to your basic physics class, you know that when you submerge an item in water, it displaces water and based upon the volume of that item. So you can think about this in your own real world context. If you take a bath and you sit in the bathtub, you know that the water, as soon as you get into the bathtub, the water rises up. It's displaced by how big you are, basically. Any object, you put any big object in water, or even a small object in water, and it's going to displace a volume of water proportional to its volume. You can exploit this Archimedes principle to measure bulk density in a rock, which is pretty great because if you think about a rock, to measure the volume of it is really hard. They're irregular in shape. They're not a simple cube. You can't just apply some simple geometric model to calculate your volume. So how this works is if you have a scale, and I show on the left-hand side here, there's a scale and I've got a little rock hanging on the bottom of the scale. If you weigh the rock just dry in air, this particular rock weighs 4.5 grams. So whatever your rock weight is in air, that's the weight of that rock. If you keep your rock attached to the scale, but you submerge it in water, you have a buoyancy force, right? So you have a force of the rock pulling down due to gravity, but you also have a resistance force, which is the resistance of the fluid up onto that rock, which is a buoyancy force. So the buoyancy force is equal to the weight of the water displaced by the rock. So if you think of the volume of water displaced by the rock, I've drawn it here as, you know, the original level of the water before you put the rock in, and that level rises when you put the rock in up to the top level here. So that volume is equal to a weight of water through the density equation, which in this case is 2 grams. So when you weigh your rock, if your rock is full of vesicles, it's full of holes, then the weight of the submerged rock, or even if it doesn't have holes, is going to be less than it was in air because it's got that buoyancy force lifting up on it, right? So it's counteracting the forces of gravity. So in this case, the submerged rock only weighs 2.5 grams. It weighs less than it did in air because of that buoyancy force pushing up on the rock, proportional to the amount of water that was displaced. So the buoyancy force experienced by a submerged object is equal to the weight of the liquid that's displaced by that object. The submerged object will apparently weigh less by an amount that's equal to the weight of the liquid displaced because of that upward buoyancy force. So you imagine, though, that in your volcanic rock, you have a lot of holes in it. So if you do this experiment with a vesicular piece of pumice, you actually have to seal the outside edges of the rock to prevent water from getting into the pores to get an accurate reading. So you can calculate bulk density from the weight data collected using Archimedes' principle. And this is the first thing you're going to do for your module. The density equation, bulk density, it's equal to the dense rock density plus the density of the pore spaces. So density, as a reminder, is equal to the mass of an object divided by its volume. The weight of an object is equal to mass times gravity. So in air, That weight is the mass of the rock and pulled down by gravity. The buoyancy force on that rock, F sub B, acting in the opposite direction to gravity, is the weight of the water displaced is equal to the bulk density of that rock times gravity times the rock's volume. So there's an apparent change in weight when the rock is submerged due to that buoyancy force acting against the gravitational force. So your dry rock weight, if you weigh your rock dry and then you weigh your rock submerged in water, the dry rock weight minus the weight of the rock submerged in water, or the wet rock weight, is equal to the water density times the rock volume. Water has a very nicely convenient density of 1 gram per cubic centimeter, so it makes it super easy in these calculations and it cancels itself out really nicely. So your bulk density of your rock then is equal to the dry rock weight divided by the dry weight minus the wet weight. Okay, so again, I mentioned that vesicular rock is full of holes. If you submerge a vesicular rock in water, it's either going to float because it has a less density than the water, or it's going to sink and the water is going to infiltrate its way into the pores and fill them up with water. So you don't want that. You want the pores to remain clean and dry and just full of air. So the way we do this in the lab is we take our porous rock sample, we take a sheet of moldable wax, like parafilm, like you would use in your chemistry lab to seal off containers of chemicals. That parafilm, you can stretch it out and you can mold it around your rock and completely seal the outside edges so that when you submerge it in water for the water weight, the wet submerged weight, you're just getting the weight of that rock with only air filling those vesicles. So your rock bulk density equation has to account for the weight of the wax sheets that you used. And if you have a little rock, you can use 1 sheet. If you've got a big rock, you might need 2 or 3. So your bulk density equation becomes something slightly different. It's equal to the weight of the rock weighed when it's dry minus the parafilm weight that you use, so how many sheets of parafilm, divided by the dry weight minus parafilm minus the wet weight plus the parafilm weight, because you remember the forces are acting in an opposite manner when you're submerging your rock because of the buoyancy force. So this is the equation you're going to use in your homework to calculate bulk density from the Archimedes weight data you're given, the dry rock weight, and then the weight of the rock measured as it's submerged in water. When you have these parameters, the porosity of the rock is really easy to calculate. If you want to calculate porosity in terms of the volume percent of pore spaces in the rock, or its vesicularity, in other words, you basically just take the density of the rock, you subtract from that the bulk density divided by the density of the rock again, times 100%. And I'm sorry, this little division symbol should be outside of the parenthesis there. Okay, so once you have your porosities and you calculated those from the Archimedes data collected and given to you, you can estimate permeability using percolation theory. I'm going to give you the constants, and you're going to use this percolation theory equation after Sar and Manga to estimate the permeability of those Okmok samples from the 2008 eruption. Okay, and finally, you're going to use your porosity and permeability results from samples collected from the 2008 eruption of Okmok to answer some questions about that eruption and to place your measurements in the context of magma degassing and explosive eruptions. All right, so I know this is a lot, and this gets into some fairly complicated modeling and measurements. But don't worry, I'll help you as much as you need, and please ask questions during chat sessions or you can email me. I do think this module is really important because this is the fundamental way that we can try to say something about what the magma degassing processes are like in a volcanic conduit before an explosive eruption. There's a long-standing tradition in history and volcanology of using natural sample data to answer these questions. So I think it's really important for even an undergraduate physical volcanology class to at least get you some introduction to how we do this, because it's a really important part of volcanology. So first of all, read through the PowerPoint slides in detail before you get started. Read the entire Word document that explains your homework before starting your calculations and models. The data are all provided for you, and they're included in the course materials section of Blackboard. But if you have on hand a scale and some parafilm and some pumice, you can try this at home. And if you want to do that, let me know, and I'll help coach you through how to do that. Basically, you just need to make a hanger for your rock sample so that you can hang it in the water bath while you're measuring its weight. It's actually pretty easy to do with just some hints. And then again, if you have any questions, don't hesitate to ask. And I hope you have fun with this module.